Humanity has always gazed at the cosmos with awe and a touch of dread. The vastness of space is the ultimate unknown, fueling myths and modern fears alike. No cosmic object embodies this fear more than the black hole, a region where gravity is so intense, not even light escapes. Black holes have become the monsters of our imagination, thanks to science fiction and sensational headlines. So when scientists built the Large Hadron Collider, or LHC, to recreate the conditions of the early universe, public anxiety soared. What if, people wondered, the LHC accidentally created a black hole on Earth? This fear sparked a global controversy, pitting scientific curiosity against public anxiety. But this story is about more than physics. It's about how we confront the unknown and whether we let fear or understanding guide us. In 2008, as the Large Hadron Collider, or LHC, prepared to launch its first experiments, a wave of panic swept across the globe. News outlets buzzed with speculation, and the public's imagination ran wild. The world's most powerful particle accelerator was about to be switched on, and some people feared it could spell disaster for the entire planet. The question on everyone's mind was chilling. Could CERN accidentally create a black hole that would devour the Earth, swallowing everything in its path? The idea was both simple and terrifying. A tiny black hole forms inside the collider, sinks to Earth's core, and begins to consume the planet from within, growing larger and more powerful with every passing moment. Lawsuits were filed in an attempt to halt the LHC's operation, and sensational headlines only fueled the growing fear. Protesters gathered outside scientific facilities, demanding answers and action. But this nightmare scenario was rooted in a fundamental misunderstanding of physics and the nature of black holes. Many people imagined that any black hole, no matter how small, would behave like the cosmic giants we see in space, those that swallow entire stars and warp the fabric of the universe. In reality, the physics of the quantum world is far stranger and more subtle than most realize. The rules that govern subatomic particles are not the same as those that apply to massive objects in space. The myth ignored a crucial fact. A microscopic black hole, if it could even be created, would be governed by entirely different rules. It would be incredibly unstable and would evaporate almost instantly, long before it could do any harm. Scientists at CERN and around the world tried to reassure the public, explaining the real science behind the headlines. But fear, once unleashed, is hard to dispel, especially when amplified by media and rumor. The stage was set for a dramatic clash between scientific fact and public anxiety, with experts working tirelessly to communicate the truth. The real question remained: could the LHC actually create a black hole? And if so, would it pose any danger to our planet or to us? To answer that, we need to look closely at the science behind these tiny hypothetical black holes and what modern physics really tells us about their behavior. And what we find when we separate fact from fiction is far less frightening and far more fascinating than the headlines ever suggested. Could the LHC create a black hole? It's a question that sparked imaginations and headlines around the world, fueling both curiosity and concern. The idea of a man-made black hole conjures images of cosmic destruction, but what's the real science behind it? Theoretically, maybe, but it would be nothing like the monsters of deep space that swallow stars and warp time. The black holes we know from astronomy are born from the collapse of massive stars, weighing millions or even billions of times more than our sun. A microscopic black hole, if it could be made at all, would be smaller than an atom. So tiny you'd need a powerful microscope just to imagine it. Its mass would be just a handful of protons, making it almost unimaginably light compared to anything in our daily lives. It wouldn't have the gravity to swallow anything, not even a speck of dust. In fact, it would pass right through ordinary matter without leaving a mark, unable to pull in even the tiniest particle. The key difference is Hawking radiation, a process predicted by Stephen Hawking, where tiny black holes evaporate almost instantly, releasing their energy back into the universe in a flash of particles. If the LHC made one, it would vanish in less than a trillionth of a second, leaving no trace behind. There would be no time for it to interact with anything around it, let alone cause harm. It couldn't fall to Earth's core or start eating the planet. The laws of physics simply don't allow for that kind of runaway scenario, no matter how dramatic it sounds in science fiction. In fact, scientists would celebrate such a discovery. It would open a window into quantum gravity, extra dimensions, and the very fabric of reality. It would be a Nobel-worthy breakthrough, not a disaster. Nature already does this experiment every day. Cosmic rays, particles from space, hit our atmosphere with far more energy than the LHC can produce, and Earth is still here, unchanged after billions of years. The science is clear. Even if the LHC could make a black hole, it would be harmless. The world's top physicists have studied the risks in detail, and the consensus is unanimous. The real danger was never in the machine, but in misunderstanding the science. Fear often grows in the gaps between what we know and what we imagine. The black hole bombshell was a myth, not a menace. It's a story that shows how science and myth can collide in the public imagination. The LHC is safe, and so are we. The world's most powerful particle accelerator is a tool for discovery, not destruction. But the story of public fear was far from over. The myth of the black hole lingered, shaping how people saw science and how scientists responded. Just as the world was beginning to move past the fears of black holes at CERN, another scientific shockwave rippled through the physics community in 2011. This time, it wasn't about destruction, but about the very nature of reality itself. The OPERA experiment, a collaboration between CERN and the Gran Sasso Laboratory in Italy, announced a result that seemed almost impossible. Neutrinos, those tiny, nearly massless, and famously elusive particles, appeared to be traveling faster than light itself. If this finding were true, it would overturn one of the most fundamental pillars of modern physics, Einstein's theory of relativity, which has stood unchallenged for over a century and states that nothing in the universe can outrun light. The speed of light isn't just fast, it's the ultimate cosmic speed limit, woven into the fabric of space and time. Breaking it would mean rewriting our understanding of how the universe works, from the smallest particles to the largest galaxies. The scientific world was stunned. Physicists everywhere were left questioning everything they thought they knew. If neutrinos could somehow escape a black hole by moving faster than light, then black holes, the ultimate cosmic traps, would lose their power. They wouldn't be able to hold anything inside, not even themselves. Stable black holes, which act as the anchors at the centers of galaxies and shape the cosmos, would be impossible. The very structure of the universe would be called into question. The claim created a direct contradiction. Either Einstein's theories, which have been confirmed time and again, were wrong, or our observations of the universe were missing something fundamental. The OPERA team knew the magnitude of their announcement. They invited scientists from around the world to scrutinize their data, understanding that extraordinary claims demand extraordinary evidence and rigorous verification. The stakes were enormous. The very fabric of physics and our understanding of reality was on the line. The world watched as the scientific process unfolded in real time. Was this the end of black holes as we knew them? Or was there a mistake waiting to be uncovered? The search for answers began as physicists everywhere raced to test, challenge, and understand this astonishing claim. The scientific community met the faster-than-light neutrino claim with skepticism. Physicists worldwide pored over the data, searching for errors. The experiment's timing relied on nanosecond-precise synchronization between Switzerland and Italy. After months of investigation, the culprit was found. A loose fiber optic cable delayed the timing signal. This tiny error made neutrinos appear to arrive early. Once fixed, the effect vanished. Neutrinos traveled at the speed of light, just as Einstein predicted. The foundations of physics were safe. The OPERA episode became a textbook example of the scientific method: bold claims, open scrutiny, and self-correction. Scientists make mistakes, but the process leads to truth. The universe's speed limit was back in place, and black holes were safe from paradox. While physicists fixed cables, the universe delivered its own proof stable black holes are real. In 2015, LIGO detected gravitational waves, the ripples from two black holes merging over 1 billion years ago. This was the first direct evidence of black holes, confirming Einstein's predictions. These were not fleeting quantum objects, but massive, stable titans that had existed for eons. Since then, dozens more black hole mergers have been observed. The universe is filled with these silent giants, shaping galaxies and cosmic history. The evidence is now undeniable and direct. Gravitational waves have opened a new window on the cosmos. Black holes are as real and stable as the stars themselves. The cosmic monsters of our imagination are now proven facts of nature. CERN is more than a black hole laboratory. It's a global hub of scientific collaboration. Thousands of scientists from over 100 countries unite to unlock the universe's secrets. At its heart is the Large Hadron Collider, a 27-kilometer ring where protons smash together at near light speed. Giant detectors capture the subatomic debris, revealing the building blocks of reality. The LHC's crowning achievement, the discovery of the Higgs boson, the particle that gives mass to matter. This breakthrough completed the Standard Model and earned a Nobel Prize. CERN's innovations reach far beyond physics, from medical imaging to the invention of the World Wide Web. The LHC's data even helped pioneer modern cloud computing. CERN is a powerhouse of discovery and innovation, sharing its benefits with the world. It's proof that curiosity and collaboration can change everything. Even the LHC has limits, so physicists are turning to the universe itself for answers. Supermassive black holes at galactic centers act as nature's ultimate particle accelerators. Their immense gravity and magnetic fields hurl particles to energies far beyond anything we can achieve on Earth. These cosmic collisions may create exotic particles, perhaps even the elusive dark matter. Some of these particles could escape in powerful jets, detectable by observatories on Earth. Instead of building bigger machines, we can use telescopes and detectors to study nature's own experiments. Projects like the IceCube Neutrino Observatory are already searching for these cosmic messengers. It's a beautiful synergy, using the largest objects in the universe to study the smallest. The cosmos is the ultimate laboratory, and we're just beginning to explore its wonders. What's next for CERN? The quest for knowledge never ends. The LHC is being upgraded to the high-luminosity LHC, set to produce 5 times more collisions and unlock new secrets of the Higgs boson. Plans are underway for a future circular collider, 4 times bigger than the LHC, to reach even higher energies. These ambitious projects will probe the mysteries of dark matter, dark energy, and the fundamental forces of nature. The story of CERN's black hole bombshell is one of reason triumphing over fear and evidence over speculation. Science teaches us not to fear the unknown, but to explore it. Whether building machines underground or studying cosmic accelerators, our adventure continues. The universe is full of mysteries, and we are just getting started.